Okay, class, today we are looking at another question on rates of reactions. We are looking at a question where you compare the rate of the reaction. You measure the rate of the reaction by looking at a change in volume. If you remember the last sum that we did, we measured the rate of the reaction by looking at the change in mass. How did the mass decrease? According to the change in the mass, we could get an answer. So I just said today, let me do another one where if we have a change in volume, you can also measure the rate of the reaction, right? So the apparatus shown below is used to investigate the rate at which hydrogen gas is produced when a 6.5 gram of zinc reacts with 30 moles of 1 mole per dm cube HCl. Right, so we've got zinc plus hydrochloric acid here, all right, and they're reacting, and what's going to happen when an acid reacts with a metal, what do we get? Salt, zinc chloride plus hydrogen. Nah? I'll just fix that up. We'll get zinc chloride plus hydrogen. What experimental method is used to determine the reaction rate in this experiment? So let's write down. What's the experimental method used to measure the reaction rate? The answer would be measuring the volume of the gas produced, right? Because we're measuring the volume of the gas that comes out. And how do you measure the gas? You measure the gas using the syringe, right? You have the syringe then. What is the gas that's released? Hydrogen. In another experiment, there may be carbon dioxide released or something like that. It just depends from reaction to reaction. So you'll have to see what you are given in the reaction. What other experimental method can be used to measure the reaction rate for this reaction? So instead of you putting a syringe there to measure the hydrogen that's released, what could you do? You could do what we did yesterday. You could measure the mass decrease, isn't it? Measuring the change in mass of the reactants. So we're putting this whole reaction mixture on a scale and measuring how the mass changes, right? Determine the limiting agent using calculations. How are we going to do that? Limiting reagent, you'll have to look at what's reacting with what. How do you work out limiting reagent? You'll have to look at the moles or the mass of what's given. So what do we have in our reaction? We've got 6.5 grams of zinc. All right, so can we work out the moles of the zinc? All right, so let's work it out. Number of moles is equals to actual mass over molar mass for zinc. And you can work out the number of moles of zinc. All right, what did we get? Did we get 0.05 moles according to this? 33.25 actual mass. This is the right one. No, it's different. Okay, we'll have to take your actual mass over molar mass for zinc. Your actual mass will be, your actual mass of zinc will be 6. The answer is wrong. 6.5. All right. So we have to take our 6.5. Does somebody have an answer for me? Can somebody give me an answer? Actual mass of zinc 6.5. What's your molar mass of zinc? Get it from your periodic table. $65. All right, so 6.5 over 65. And what do you get? 0.1. Correct. Somebody talk to me. 6.1 moles. Right. And then if we go here, we'll see that if you look at the mole, the ratio at which they react, this is a balanced equation. ZnCl2. This is bad today. ZnCl2 Don't make silly mistakes like that to mess the whole sum up. Usually they give you the equations, the balancing numbers. Sometimes they give you, sometimes they don't give you. So you must just double check, right? ZnCl2 plus H2. So that gives you 2 HCl. That's correct, right? So 1 mole of zinc reacts with 2 moles of hydrochloric acid. Now we know that according to ours, we got 0.1 moles of zinc. So how many moles of hydrochloric acid will there be? 1:2, isn't it? 1 zinc reacts with 2 hydrochloric acid. So we've got 0.1 mole of zinc, which means that we'll have 0.2 moles of hydrochloric acid. 2 moles of hydrochloric acid. So that will be 0.1. This is not right. All right. So that's we've got 0.2 moles of hydrochloric acid. So the number of moles of hydrochloric acid is equals to 0.2 mole HCl. All right. And now we got a number of 2 moles of HCl. Now what we can do with the number of 2 moles of HCl, we can say N is equals to C times V. According to this, we've got our volume, and we've got 30 moles of HCl. 30 moles of HCl and 1 mole per dm cube. So the way they did it in the memo, they say, okay, we've got 0.1 moles of zinc. Let's see how many moles of HCl we have. So you can use the other equation. You can say number of moles equals N is equals to C times V. You got 2 moles of zinc, and you got 30 moles, which is 30 moles will be 30 centimeters cube, right? Divide by 1,000, so it's 30 divided by 1,000 because it's dm cube. And you see you got 0.06 moles of HCl.
Sorry, Ma'am, why does it say 2H2?
Where? Here? It's wrong, nah? It's supposed to be
Yeah, what?
Zn plus
Just H2.
just HCl, isn't it? Yeah, that's correct. Correct. Right, Zn plus HCl gives you ZnCl2 plus H2. That's balanced. Okay. You're working with me. What am I doing? It is correct. Just check it properly. So we've got 0.2 moles of HCl. That's reacting. So, no, not 0.2 moles. Number of moles of HCl will be 2 moles, right? So what the mole ratio is 1:2. So if you got 0.1 mole of zinc, that means 0.2 moles of HCl will react. Right? You don't have to do this long story also. So then which one is the limiting reagent? Which one is finished first? Let's just figure this up. So the number of moles of HCl. Okay, we can take, you don't need this part, you can even take this part out. Né? Got number of moles of zinc is 0.1, the number of moles of HCl will be 0.6. So therefore, we can see that the HCl is the limiting reagent. How did they get that? Because, how did they get that, anybody? Because if you take your HCl and you times it by 2, even according to the balancing number, you just see Zn is 0.1, then your HCl will be 0.06, 0.06. But how much of HCl do not 0.06? You needed how much? You needed 0.2 HCl. But if you had 0.1 of, if you had 0.1 mole of zinc, right? It means that thus you need 0.2 2 mole HCl. All right. But what do we, how much moles of HCl do we have? We worked it out. We only got 0.06 moles of HCl. We're short. Therefore, HCl is the limiting reagent because it gets finished first. All right. In your head, you'll say because it was used up first. This is in your head. All right. Going up, question 4. Write down the name of the flask labeled Z. This is the flask labeled Z. What's it called? The flask labeled Z is your conical flask, or it's your Erlenmeyer flask. That's another name that they use. Conical flask or Erlenmeyer flask. All right. Conical or Erlenmeyer flask. And then number 4.2, one function of the item of apparatus label Y in this investigation. So what's the apparatus label Y? It's a syringe, it's a gas syringe. And what's the purpose of the gas syringe? All the hydrochloric acid that reacts with the zinc, the gas that's given off here, the hydrogen gas will be collected by the gas syringe. So it's to collect and measure the hydrogen gas that is released. It's used to measure the hydrogen gas that is released. Measure the volume of the gas produced. Okay. Question 5. From the table above, write down the independent variable for an investigation and one control variable. So the independent variable will be time because you can't control the time, right? So the time will be your independent variable, and your control variable, the variable that you will see that is changed, will be what substances will you keep the same control. You keep the mass of the zinc that you put in the flask the same. You'll put going outside. Right, go now. You put the mass of the concentration of hydrochloric acid the same. So yeah, those two seems to be the most best for control variable. You'll keep maybe the temperature the same. All right. So let's see what it says here. 5.2. Temperature of the reactants. All right. 5.1. What's the question? From the table of the independent variable. The independent is what I change. Are we looking at a 2 experiment? Sorry. If you're looking at a 2 experiments, the independent variable would be what you change. All right. So what did you change? 25 became, in experiment 1 is 25, and 40 will be experiment 2. So what did you change? You changed the temperature. All right. So the temperature of the reactions is what you change. And according to the change in temperature, what is the control variable? The control variable that you leave the same, the concentration of your reactants, the number, the mass of your chemical, and the concentration of your hydrochloric acid, the mass of the zinc, the concentration of your hydrochloric acid will be your control variable. So you changed independent variable is what you change. You change the temperature, 25 and 40. So your independent variable is your temperature. Right? What's the next question? Sorry, I'm going so up and down, messing things up here. Question 6. The volume of hydrogen gas produced is measured in each experiment. The graph below is the results obtained. So sometimes they will give you a graph paper here and they'll give you a table and they'll ask you to draw the graph. Right. And sometimes they'll ask you to draw another graph for 40, 25 and 40. So if you look at this graph, if you didn't have the P and Q, which will be the 25 at the temperature of 25 and which will be at the temperature of 40. All right. You got a 25 and a 40 here. They're both powdered. In some cases, they'll make the one lumps, right? Instead of powdered. Then which one will be faster? So you'll have to look at the time. So they say in question 6, which graph, P or Q, represents experiment 2? Refer to the data given in the table as well as the shape of the graph to explain how you arrived at your answer. So experiment 2 is what? Experiment 2 is the one done at 40 degrees. So the question is, will the reaction at 40 degrees take place faster or slower than the reaction at 20 degrees? So what do we know? What factor affects rate? The temperature. So the temperature of experiment 2 is higher. So therefore, it will be a faster reaction. So a faster reaction means that the reaction will complete faster. So looking at the time from P and Q, where is the time of the reaction complete faster? How do you know when the reaction is complete? We must look at when the graph is flat. All right. So if you look here, the graph becomes flat. The graph becomes flat. For P, where does the graph become flat? Let's just put it down. Where's this thing now? Here. Where we're writing. Becomes flat there, right? And then for Q, where does Q become flat? It only starts becoming flat there. Right, so which one became flat earlier? Where flat means that the volume stays the same here, right? Is where the reaction has reached completion. So if you look at this one, it's reached completion here at this time interval. All right. And if you look at the other one, it's completed, it's reached completion here. So what happens? The time interval is earlier. So the reaction that reaches completion earlier will be the blue one. So that's P. It gets flat earlier. So which graph, P or Q, represents experiment 2? Experiment 2 is the one that completes earlier. Nah? So let's see which one was that. Experiment 2 will be the one that completes earlier. So that will be P. P will be your answer, right? Question 6, we'll get an answer of P. All right. And then do they want an explanation? Let's see what's the question again. Refer to data given in the table as well as the shape of the graph to explain how you arrived at the answer. All right, so what will you say? Because the concentration is higher, the time for the reaction will be quicker. Experiment 2 has a higher temperature. The same volume of gas was produced in a shorter period of time. The graph got flat earlier, meaning that there was no more reaction taking place. All right. Or another way of saying it would be that you could have said experiment 2 has a higher temperature, so the graph has a steeper slope. All right. So if we look at it, this graph has a steeper slope. I don't like the second answer. I prefer the first answer. If you look at this graph P, it's a steeper slope and then it becomes flat earlier, right? And Q has a slope that's not so steep and it comes to completion later when it's flat here on the top. All right. So we've got the answer for the question 6. Question 7, give a reason why the rate of the hydrogen production was slows down towards the end of both experiments. Meaning that if you, how do they know that the rate of the reaction is slowing down? Is because if you look at the steepness of the slope here, it's high, right? And then if you go here for both graphs, if you take the steepness of the slope here, for example, right, you're taking a tangent to the slope there, you see that the tangent is less. So the tangent gets smaller. So why does the tangent get smaller? It's because there's less reactants to react. The reaction rate slows down because the concentration of the substances are getting less. The substances are getting finished. So there's less particles to react. There's less effective collisions. The rate slows down because the concentration of the reactants decreases. All right. Let's see what they say for us. Let's just clear everything. Question 7. So the answer that they gave us, the concentration of the reactants decrease as the reaction proceeds. All right. So that's why the slope is getting less steep because there's less reactants to react in the reaction. Okay, and then question 8. Calculate the mass of zinc used to prepare 0,024 dm cube of hydrogen twice. at room temperature. Assume that 1 mole of hydrogen has a volume of 24,04 dm cube at room temperature. Okay, how will we do the sum? Calculate the mass of zinc used to prepare 0,024 dm cube of hydrogen at room temperature. Assume that 1 mole of hydrogen has a volume of 24,04 dm cube at room temperature. So to do the sum, again, we're going to be looking at stoichiometry of last year, and they will definitely ask you this type of questions this year. And they'll relate it most probably to this section, right? So what we can do here, we can work out the moles of hydrogen that we've actually got in our section, in our question. Right, so how much was we prepared? 0,024 moles of hydrogen. So how many moles is that? So we work out number of moles is equals to actual volume over molar volume, N is equals to V over Vm. Your actual volume is 0,024 and your molar volume is 24,04. All right, and what do we get? What's the volume of hydrogen? And then we must compare the moles that we've got. Let's see what we did. 24,04, 0,24, is it 0,24? 0,024, the answers are wrong here. 0,024, 0,024 over 24,01, 24,04. I don't have a calculator in front of me. Can somebody give me this answer? So 0,024, let me take it on myself. Somebody not helping me? 0,024.
Madam, I got 9,98 times 10 to the minus 4.
Doesn't sound right. Let me check. Somebody else?
Mustn't it be N is equal to V over Vm?
Yeah, and then what you'll get?
And then you'll say V is 0,024 divided by 24,04 gives you I got 9,98 times 10 to the power minus 4.
You got the same.
Maybe
You got the same answer. Right, V over Vm. So this answer will be what you said. Faizan, you had the answer. What was it? 9 comma. Shoaib, give me that answer.
9,98 times 10 to the minus 4 moles.
Right, so that's the number of moles of hydrogen. And then what do we know? 10 to the minus 4. We know that the mole ratio of zinc to hydrogen is 1:1. Where did we get that from? If we go up here, zinc is to hydrogen, we'll say zinc, it's 1, right? And hydrogen is also 1. So the mole ratio, you must compare the relevant parts, zinc with hydrogen. So the mole ratio is 1:1. So therefore, the number of moles of zinc will also be 9,98 times 10 to the minus 4 moles, right? And then we can work out the number of moles of zinc now. Well, what's the question actually? We got a number of moles of zinc. We must calculate the mass of zinc, right? So then we know number of moles of zinc is equals to actual mass over molar mass. So work it out for me. We got a number of moles of zinc, 9,98 times 10 to the minus 4. Right, because our number of moles is 9,8 times 10 to the number 9 is 4. Is equals to actual mass is what you want to find. The molar mass is 65. And what's the answer that we get there? Can somebody give me an answer? Shoaib, you're with me? Give me the answer.
When we get 0,06.
0,06. What's the next decimal, Faizan?
4.
4.8.
4. So then it's right. Right. So the answer will be 0,06 grams. Can you confirm that? I think it looks right. Okay. So that will be the answer. That's the way we can do it. 0,06. Okay, they got a variation here. Let's just look at the variation. 1 mole of hydrogen is 24,04. Therefore, 0,0, did they want 0,01 moles of hydrogen? Is 0,24, 65 grams is 1 mole, so therefore 0,065, 0, you can check this on your own time, right? There may be a mistake there somewhere. Because our moles wasn't 0,01. Okay, I'm just going to leave that there. I've sent this to you so you can just double check. So the answers that some of them I sent you were not correct. Okay, so if we're going further, we're done with the question. So just to look at this question again, we see that they can ask you mass or volume. They can even give you, instead of them giving you the reaction experiment, they can give you a graph. They can start off with a graph. All right. But in this question, they gave you the equipment, they gave you the equation, then they asked you questions relating to the rate. They can ask you to calculate the rate of a reaction. They will say reaction rate over time, like how we did yesterday. Then they can ask you questions on stoichiometry, very important, determining the limiting reagent. They ask you the name of the apparatus, not so common. And they can give you a graph to add to this. I could have put an experiment 3 here and said lumps of zinc, right? 0,2 mole per dm cube hydrochloric acid, temperature 25 degrees, right? Then I can say use experiment 3 and draw it on a graph paper provided. Then you'll have to take this graph paper and see where will it be. Will it be higher than Q or will it be lower than Q? You'll have to see all that. So it will be lumps. So say, by the way, if you use lumps, where will the graph be? Will it be a faster reaction or a slower reaction if you use lumps? All right, say we use lumps. Lumps, I'm writing lumps here. Let's see if I can write. It's not going to write. So if I use lumps, it's going to be a slower reaction, isn't it? It's going to be slow. So how will it look on the graph? I don't know why this thing is not writing. So if it's a slower reaction, how will it look on this graph if you had to draw it? The reaction will take longer to finish, right? So the reaction will be somewhere like this. Let's see if we can write. No, it's not writing. And now, it doesn't want to write. I don't know what I must do. It's not letting me write. It will end up basically here, somewhere there. All right. So then we can say that the reaction will take a longer time to finish. Okay, so I'm going to leave it at such. I can't just draw on this graph for some reason. I don't know what to do. See it when they're yellow. So it won't be here. No? The graph will be, it will be, the yellow one is wrong. The red one, let's see if we can get, let's try one. It will be later. Okay, it's not letting me write. Okay, so it will end up later, no? Yeah, so the graph will be below Q. There's it. I don't know, it came now after action. It will be below Q. And it will end at the same time, no? It will end at the same time. Why will it end at the same time? Because you have the same amount of reactants and products. But say I used half the amount of zinc. I use less zinc, or I use less, the hydrochloric acid was less, then in that case, the volume won't end. At the end here, the volume will be less. So you'll get a graph that finishes up early. So graph will go up like this, and then it will get flat here. It will get flat there. It will be like that. Okay. So they can ask you that as well. It's a pity I can't draw here. I would have just put the graph basically will be, I'm just going to put it there like that. It will have ended up there halfway or something because the reactants get finished early. Okay, I just don't know. Oh yeah, here's draw. Let's try. Sorry, mouth. So it will go like this. And then because it's over now, we should have taken this one actually. Because the reaction is over, then it will end there. So that's if you use half the amount of reactants. But the one we did, we see that it was, if we use lumps, then it will go up and it will end there. Flat graph, right? So that's important. If it's the same amount, then it will end flat. The graph mustn't look like, so I saw graphs that look like this. One person puts a graph like that, then the other graph goes like higher up, no? Because you have the reactants that are the same, you can't get a graph that's higher up or lower down. It must end at the same time, all right? Just remember that it must end at the same time. I'm having tough time here drawing. All right, so you can't have graphs looking like that over each other. They must all end at the same time. Remember that. Okay, we will stop there with this question now.